Hello students, a very warm welcome to JEE English by Unacademy, India's leading and largest test preparation and learning platform. Guys, this is the first channel across the nation that delivers content exclusively in English for your JEE preparation, be it your JEE Advanced, JEE Mains, BitSat, etc. And guys, let me tell you something. This channel has the best-in-class educators who have graduated from premium institutes and they know what you need to do to get the fundamentals and to crack the exam. And not only that guys, we'll take you from the basics until the depth of every topic and you can sit around and enjoy. Even if you're a hustler, you will enjoy this channel. We will take you through all the applications of every topic that we are teaching you. Alright guys, the topic of the day is current and electricity. A very interesting topic. Not only that, it carries a good weightage and it is independent of rest of the topics. Which means you can learn this topic separately, be it you're in 9th class, 10th class and 11th class, if you're preparing for exam, and you can still score good amount of marks when it comes to current and electricity. And guys, you know all about current and electricity, I know that. But what about the different expressions? Like what is going to happen when you're applying field? What is this new terminologies that you're going to come across when we are talking about current and electricity? And we are going to explore that. And today we are going to cover some bits and pieces of this current and electricity. And throughout this lecture series, we will cover every single bits and pieces of current and electricity. I will take you from the basics until the depth of the topic. Alright guys. For people who know me before, well and good. Myself, I am Murlidharan. I completed my MS in Electrical Engineering from University of Colorado Boulder and I am an electrical engineer and I am an IITian as well. And I have 4+ years of experience preparing students for IIT JEE and other competitive exams. I have filed 22+ patent applications in India, US and Canada, and today I am here so that I can take you through this current and electricity and one of the most crucial and important part of current and electricity. You will love this topic guys, you will love physics, you will love this topic as and when we keep going into this topic. It's a pretty lovely topic, it's very easy. As I would say this every time, but don't think that, I'm just saying it, but actually this topic is very easy and physics is really easy. It's very intuitive, guys. Physics is one of those subjects which is very intuitive. And myself and Unacademy have something very interesting for you. That's our JEE English channel. You can, go on to Telegram app. If you don't have that app, you can go and download it on App Store or Play Store and type in t.me JE_English. And you will get timely updates on our classes and schedules, and more importantly, you will also have access to the video books over there. It's going to be an awesome journey guys. So what are you waiting for? Download this app, get onto our channel, and what are you waiting for guys? Subscribe to the channel, click on that bell notification guys, share this channel. This is one of those channels where we are trying to overcome these language barriers across the nation and making sure that everyone gets access to quality education. So what are you waiting for guys? Subscribe, click on the bell notification and share it with your friends, share it with the people you know, share it on the social media. And guys, myself and Unacademy have something really special for you. That's our Unacademy Learning app. You can get onto our Unacademy Learning app and attend free live special classes from our top-notch educators. And guys, you can go to Play Store and App Store and download our app. And we also have something interesting for you on that app itself. You can, opt for a test series or you can take an academic subscription where you get live quizzes, leaderboards, polls, live evaluation and more importantly, doubt clearing sessions with our top-notch educators who are experts in this field, who are experts in exam preparation, who are experts in topics, who know it really very well. And guys, if you are looking for IIT JEE, you may want to go and choose this program specifically, IIT JEE. Else you can choose your personal goal that you are looking for. It's a very personalized platform. And guys, if you are looking for some instant 10% discount, you can make use of Murli Live coupon. And if you are in 9th or 10th class, you may want to go for 24-month subscription. Even if you are in 11th class, I think it's a 2-year-long journey. It is a 2-year-long journey and it hardly costs 1,500 per month. And if you are long-term, you may want to go for 2,500 per month. That is a 12-month package. Else, if you are in stuck in a lockdown and if you are looking for some quality education materials, we have over 6,000 plus education materials just for IIT JEE preparation. So you can even go for that. 1 3-month package hardly costs 6,000 and 5,000 per month. And guys, choose it wisely. And let's go for the topic of the day. That's our current and electricity. But before that, we will have a look at a quote from a genius. So this genius said that genius is only 1% inspiration and 99% perspiration. You got to put in that hard work. Your inspiration to crack the exams, your inspiration to gain the knowledge is not all enough. You need to put in that hard work. You need to get on to it to make it happen. And guys, let me tell you a specialty of this topic. This topic is about 1% perspiration and 99% inspiration. It's a very, very easy topic. You don't have to sweat and it's very easy. You will learn it very, very easily. It's quite a very easy topic, guys. Alright, guys, let's get started with some of, like a recap. What we have discussed, and so that you need not, get little bit trouble during the lecture. But these are some things that you know very well. So, what is current? Current is not a vector, it has a direction. Just like what you're seeing over here, the direction of current is opposite to the direction of flow of electrons. And the direction of current is also in the direction of flow of positive charges. If there are any positive charges flowing in this, like any material, then you would take that the current is flowing in the direction of that positive ions. And remember this, guys, current is not a vector, it's a scalar, it has a direction. Even though it's not a vector, it has a direction, and the direction is determined by the direction of flow of charges. And that is what tells you like current has, like a direction, because you can add them just like, how do you add numbers, but you don't add them in a vectorial way. And the most important and the very important point to remember is charge is always conserved. Like the amount of electrons that is deaccumulating in a particular, let's say dx area or dA area or dV volume, that is also getting accumulated again. So once this charge leaves these places, like when it is getting deaccumulated, then it is accumulating back again. And how do you find out current? It is the rate of flow of charges. So it's basically going to be dq by dt. Delta q by delta t, dq by dt is generally used to denote, like instantaneous things, but sometimes they also interchange things. You can call it delta q by delta t, the amount of charge that is changing, in a particular unit volume or unit cross section in an instance, like at that instance or for that whole time. And what is the other way of describing it? You can also describe it using the number of changes in charges, delta n by delta t per unit time, that is the rate of change of charges, and you can simply multiply it by the value of that charge. And if it was electron, it would be minus En delta n by delta t. So you're concerned about the direction of the current while you're assessing the current. Okay guys, while you're assessing the current with respect to rate of flow of charges or the direction of flow of charges. What about instantaneous current? Instantaneous current is the position where the dq by dt or the delta q by delta t becomes, the instance where the delta t or delta dt becomes zero, tends to zero. That instance, that moment, you're just assessing, like at particular instances, what is happening. So there is a difference between I average. When we are generally talking, we are talking about I average. We are hardly talking about, like the instantaneous current. But instantaneous current is the one where that time frame within which you are assessing the current tends to zero, not becomes zero, but tends to zero. Maybe like 1 second sometimes if it is, a constant change with every second, or else it can be some microseconds. And how do we denote the directions? Like how do we denote it on a paper, guys? How do we denote the direction of current on a paper? If you denote it with an X, that means current is flowing inside and the electrons are flowing outside. And if you denote it with a dot, that means the current is flowing outside and the electrons are flowing in the inward direction. Okay guys, I hope you got this point. It is very clear. This is, like a small brief on the current itself. And this is very important to know. The most important part to remember in this is current is not a vector, but it has a direction. And the direction is in the direction of flow of positive charges, or it is in the opposite to the direction of flow of electrons or negative charges. And the other thing you have to remember is what is the representation or the expression of current. That would be delta Q by delta T, and if you make this delta T tend to 0, then it will become instantaneous current. And let's now do a thing. I think we have solved a similar problem last time, but this would give you, more of, an intuition what we were doing the earlier time, because the earlier time it was just written in terms of, words and letters. This time, you are having an awesome representation of what is happening so that you can understand it better. See this red color thing, this red color charge is moving in the circle, right? It's moving in the circle. It's awesomely moving in the circle, I guess, in the clockwise direction. And this circle has a radius of r. So let's first read the question. And guys, keep doing it, keep writing it down, comment on the comment box or in the live chat. You should be active during this time. And especially if you're preparing for the exam, you should be very, very active. Even if you're learning the concept, you should be very active. And this is actually a conceptual question more than like a numerical or a problem itself. Okay guys. So a charge minus E moves with a constant speed V in a clockwise direction in a circle with radius r, like what is being shown in the animation. Then find the magnitude and direction of current. Okay guys, how do you do this? The simplest way to do it is, students, you need to assess the time period. Because you see, let's say this is the point that I want to assess. Okay, this is the point I want to assess. This charge completes this entire rotation and comes back to this point at a specific time instance. In this case, the speed is constant, means it has a definite time period. And why are we assessing the time period? We are assessing the time period because this charge is going to appear at that position after that specific time frame. For assessing the current, we are assessing the flow of charges. And in terms of expression, it is nothing but delta Q by delta T. What does it say? This change in charges can be with respect to time. Even if it is one charge, if it is appearing at different times, at a particular time period or even different times at a specific position, that means there is a flow of current. A really very hypothetical problem, but understand this point very, very, carefully. That when I'm talking about, the non-traditional but a basic question over here, a basic concept where this charge is flowing in a circle, once, let's say this is the point, then this charge is completing this entire, the circular motion coming back to this point again. And in this case, it's a uniform time period, okay? Because it is flowing with, it is moving with a constant speed V. So that means at that specific position, it is appearing again. There is a rate of flow of charges. There is a rate of flow of charges. And very easy, very intuitive. How to do this? You need to find dq by dt or delta q by delta t. Rather, I would say delta q by delta t. If you do, because the general representation of dq by dt is saying that, delta t is tending to 0. So we are not doing an instantaneous thing. We are doing, like an averaged flow of current. So what is happening? Like, how do you find out this time period? The speed, that constant speed. The circumference of the circle. Then the time period is very easy to find. You basically divide the speed by what? Circumference to find out the frequency. Okay. And 1 by frequency is nothing but time period. Okay guys. So time taken would be 2 pi r by V and the frequency would be V by 2 pi r. So if you directly multiply the frequency, in this case it's a uniform frequency, you can directly multiply it with the value of charge, which is minus E. You would get the current flow. Okay, you get the value of current. But it is minus E into V by 2 pi r is the answer that you got over here. So this 2r is just given to confuse you. So these both are not the answers. The options were E into V by 2r in clockwise direction, E into V by 2 pi r in clockwise direction, and E into V by 2r in anti-clockwise direction and E into V by 2 pi r anti-clockwise direction. So you understood that the first term is talking about magnitude, and you know the answers are not E into V by 2r. So we have cancelled out both these options. Both these options are not relevant to our analysis. And anyway, let's not go by the options. Let's solve it, using our conceptual methods and more of our intuition. So now it's E into V by 2 pi r is the magnitude of flow of current. But what about the direction of current? See, this is a negative charge. If this is flowing in clockwise direction, or it is moving or rotating in clockwise direction, then the current is going to be in the anti-clockwise direction. Okay guys, so D would be the answer. It is E into V by 2 pi r in anti-clockwise direction, because the charge is this is a negative charge which is moving in clockwise direction. And even if you apply the sign convention, you get the same thing. So here is a method where I'm just explaining it using too much of like representations. I'm saying that there's a charge that appears in x and y. After time period t, again it appears at x and y, and the time period is what we calculated, and you have to divide the time period by the charge, the amount of charge that is appearing at the time period. Then you will get the current. And if you do it even numerically, you will get a minus for the value of current, minus E into V by 2 pi r, which is nothing but indicating it that it is rotating in the current is in the opposite direction, anti-clockwise direction, if the minus E is moving the clockwise direction. Pretty intuitive, pretty easy, nothing complicated, but a very hypothetical problem and an interesting problem. Very, very interesting problem actually. Alright guys, let's understand current density and the relationship between current density and current, because these are some things that we need to understand before getting into the crucial concept of the day, Ohm's law. So what is current density? Current density is nothing but a vectorial quantity. Like you're seeing in the animation, it's a vectorial quantity. It has a direction, it has a magnitude, and its magnitude is nothing but the current per unit area, or rather rate of flow of charges, per unit cross section. And the direction of current density is going to be in the direction of flow of positive charges, or in the opposite direction of flow of negative charges. And how do you get the intuition of current? Current is a scalar quantity which is nothing but a dot product of two vector quantities. One vector quantity is current density, the other one is area vector. An area vector has a direction perpendicular to the surface of the area. Generally perpendicular to the surface, always perpendicular to the surface of the area. Not generally, it's always perpendicular to the surface of the area. Okay guys, it's very, very easy, very, very easy. This means if the current density is parallel to, is along the surface, that means the angle between the area vector, because it is perpendicular to the area, that means it is also parallel to the flow of current density, direction of current density. That means I is equal to J into A, where I is the current. Okay, you usually do this, to find out I. This is the way to do it. This is the proper way to do it. This is the most appropriate way to do it. I is equal to integration of n cap dot j dA, where dA is the elemental area and NA is along the area vector direction and J is the current density. You are taking the dot product of n cap and J. J is the vectorial quantity current density. And you take the dot product, you get the cos theta. And I is a scalar quantity, you're not worried much about its direction, but in this case, actually you're worried about direction. Do remember this. Do remember this, because if you add current in opposite directions, you're not just going to add the magnitudes. You're going to take the sign convention into account. It's very critical, it's very, very crucial. So I is equal to integration of j cos theta dA, where dA is the elemental area. dA is the elemental area. Awesome guys, easy, very easy. Now let's say I've tilted the surface area. I've tilted the surface area such that the current is flowing like this. I've tilted the surface area at an angle to the flow of current. Now you take the projected area in this case. Okay, let's say this is the way initially that surface area was. This is the way initially the surface area was. Then in that case, you would notice that you are not really concerned about this total area, but you're concerned about this projected yellow color area. You're concerned about this projected area. Okay, I told you the analogy. It's like you're seeing as if the current is only flowing through that projected area, not to this entire surface area. It does not matter like if the surface area is tilted. You're only concerned about the direction along the flow of current. The area along the flow of current. And the area vector in this case is n cap, which is going to be perpendicular to the surface area. If it's tilted, it's like this, actually outwards. And the angle theta is there between, there's an angle theta between the flow of current and the area vector. Then in that case, you can either do the projected area thing or do even a dot product. Even doing a dot product will also let you know about it should be a cos theta. Or you can do, like take a projected area and calculate the current density. To calculate the current density, you take just the area, parallel to the flow of direction of current and perpendicular to the vector, area vector. Here perpendicular means perpendicular to the area vector. Sorry, parallel to the area vector, perpendicular to the area itself. The area that is perpendicular to the flow of direction. So it's rather intuitive to keep it as parallel to the area vector, because we will get more used to area vector as we are talking about current density. And it is nothing but projected area and J. J is the current density, which becomes I by A cos theta. You can either call this A cos theta as projected area, or even if you take a dot product, you will get the same thing. And if you take this cos theta is equal to, in this cos theta, theta is equal to 0. That is where you're saying this area vector and the flow of direction of current or the flow of current density are parallel. That means theta is equal to 0 and cos theta is equal to 1, which makes J is equal to I by A, which gets us to that expression J into A, I is equal to J into A. Okay, quite easy. Now we will explore something very, very interesting. This is this free electron model, or the electron model which looks like the gaseous model. What it says is basically, guys, if you haven't heard this model before, be attentive. I will just give you a very short brief about it. See, what is happening when these electrons are in a conductor? There are many free electrons, many free electrons, and these free electrons are moving in random directions, but with a very high speed. And why is this happening? This is happening due to the thermal energy, that inherent thermal energy, which is giving it the kinetic energy to move around, just like as in gases. Like it is always doing this Brownian motion. They're moving in random directions. But what is happening is, like, even though these electrons are moving around, they're cancelling out each other's momentum or their momentum themselves over a period of time. So even though the electrons are moving with a very high speed inside a conductor, an isolated conductor, without any potential difference applied across the isolated conductor, they are not able to generate any electric field. Really simple, isn't it? The concept is awesome, very much awesome. It's it's lovely to know about the atomic level interactions of the electrons and the atoms inside those material. So this gives you just about that the gaseous model that we have studied before, or rather let's call it a Brownian motion, like what is happening inside this electrons. Okay, guys, and what would be the thermal energy or the kinetic energy of electron be proportional to temperature? Isn't it? Because I'm talking about the energy due to that inherent thermal energy. That means Vrms is proportional to root of temperature. You can rather write it as half m Vrms square is equal to 3 kT by 2, and you will exactly get that the value of Vrms, which is nothing but root mean square velocity of the electron is nothing but under root of 3 kT by m. If you work it out for room temperature, it would be like 1.16, I guess, or 1.6, I'm not sure, but it is 10 to the power 5 order, 10 to the power 5 meters per second. I told you, right? Very high speed. It is moving around with a very high speed. And the total momentum of electrons is going to be zero if you add all the momentums or add all the velocities of the electrons inside, like a particular unit volume. You will come to know that it is not able to generate any electric field because they are in random directions which are cancelling out each other momentum, which also makes sense because there is no external electric field that is able to give them a direction. Okay, guys. So if you take the U average or the velocity average of the electron without any potential, it is going to be zero. Average velocity of all the electrons. Awesome. Now let's do a thing. Let's apply the potential across these terminals. So what is happening once I am applying this potential? Once I am applying the potential, it is still not able to move very smoothly. If you look at it from an atomic level perspective, the electrons are not still moving very smoothly. There are these vacant, spaces in this atom or in a material that is often keeping on, attracting the electrons, and the electrons are repelling themselves and they are moving around. They have a direction now, even after applying this, voltage, that you see this plus sign and minus sign and the plus sign. So now they have a direction. So the electron is flowing from minus to plus, which makes sense. And they have a direction now. From minus to plus, they are flowing in the direction. But still they are not able to accelerate fully. See, let's say I have given this voltage. Okay, you know that the initial velocity is 0. If you apply V is equal to U plus AT, then shouldn't the final velocity be accelerating with time? But it is not happening because the electrons are drifting, not smoothly, but they are undergoing some sort of collisions. You can call it a collisions. They are undergoing some sort of collisions. And they are moving under external voltage but under a constant velocity rather than a constant acceleration. But you have to understand it like this. Like once this collision is happening with an electron with a vacant positive shell, and then these electrons are getting repelled by themselves, another electron is coming. What is happening is it is slowing down, coming up, slowing down, coming up. This acceleration is there. It's a constant sort of acceleration, but this acceleration is not able to deliver any sort of increasing velocity. Rather, it becomes like a constant velocity. And we call this constant velocity as drift velocity. The velocity with which these electrons are drifting after applying the voltage. Okay? And how do you calculate this acceleration? Basically, take up the force by mass because F is equal to ma. And what is the force in this case? It's an electromotive force where you call it Q into E external, which is nothing but external field applied. Q into E external gives you the acceleration. Q into E external gives you force divided by mass gives you acceleration. And minus of it in this case because, why guys, why is it negative? Why is it negative? It is negative because it is electrons. Okay. Easy. Awesome. Q is equal to minus E rather, easier way to, do it. Now we understood that there is something known as current density, there is electrons always moving freely inside, a conductor, and apart from that, when you apply even a voltage, they are drifting only, even though they have a constant acceleration. Awesome phenomenon, isn't it? Like naturally things are awesome, even though we are trying to manipulate it, the electrons are not going under those kind of motion. But what would have happened if the electrons were, accelerating with infinite velocity, let's say? Like there wasn't any drifting happening, the electrons are moving with infinite velocity. What is going to happen? The current is going to increase tremendously, which is not safe to us. Which makes more of a sense when we are understanding this phenomenon. Things are designed, to keep us safe. Like, things are awesome. And physics is one of those things that explains how this nature is designed to, help us manipulate things for leveraging for our advantage. So other thing that we know is like, relaxation time. Relaxation time is nothing but the time between two successive collisions, or you can call it like, the phenomena where it is getting attracted by that positive vacant cell and then going out due to, again, an electron coming in the direction. The time frame between this accumulation, deaccumulation, but at an atomic level. But what is this? The mean free path? Mean free path is nothing but that path of the electron. It's a mean path. It's not, you're not going to calculate each of those paths, but you're going to calculate each of those paths, add those lengths, and take an average. That is known as mean free path. And the relaxation time is nothing but average of that time between which these collisions are happening. And you would basically substitute t is equal to tau. So guys, remember this. As and when we keep moving into the concept, remembering the formulas will become very tough, especially in this kind of subjects. Kinematics is very intuitive. We have been reading since 9th class. It's a very easy formula. V is equal to u plus at, v square is equal to u square plus 2as, and the other one like s is equal to ut plus half at square. But here, if you try to remember in terms of n, e, a, something that is going to confuse us a lot. So it's easier to remember that we are making use of v is equal to u plus at equation to derive initially the acceleration, and then to derive the drift velocity, and you are calculating the acceleration from f is equal to ma, and you understand this phenomenon why it is undergoing drift velocity just because the electrons are not moving like what we are thinking. And one other thing that you can do is you can substitute this E in terms of potential, where potential or the voltage is equal to E dot L minus E dot L rather, and then you would get drift velocity in terms of potential, which is going to be E V M L into tau. Tau is the relaxation time. Okay, guys. And what about expressing current density in terms of drift velocity? Drift velocity, you understood the concept of drift velocity. Now you would have to know some other material properties to express this current density. The kinematic thing that is happening over here is drift velocity. The rest is like material phenomena, either you are manipulating or they are present naturally. So what is current density? Current density is very intuitive when you are deriving it in terms of drift velocity. The drift velocity is making these charges to move at some unit time. Rate of flow of charges is what is going to happen due to the drift velocity. Okay. Now, if you have an electron density n, then you are going to basically multiply it to find out rate of flow of charges, but you are just finding out the rate of flow of number of charges. Then you have to multiply it with either the value of the charge or the value of the electron in this case, because we are talking about conductor where electrons are the conducting particles. So you multiply it with into minus NEA, minus E, that would give you minus NE into V drift. Okay. And when we are talking about current, we are not concerned about the direction exclusively. You are concerned about the direction of flow of electrons or the direction of flow of current. But you are not talking in terms of vectorial quantity. Okay, you are not concerned about the vectorial direction. Whereas in current density, you are very much worried about the vectorial direction. Okay. In current, you are just worried about the parallel direction to the area or the perpendicular direction to the perpendicular direction to the area and the perpendicular direction to the surface. So basically multiply this current density into area to get the value of current or the magnitude of current along with even directions. And directions you can even find out intuitively for current. It's very intuitive, it's very easy. So this is very easy to remember, or very easy to, you need not even remember. If I tell you, there are electrons moving with certain velocity. Okay. But there are these many number of electrons per unit volume. Okay. How do you find out the current? Simply you will multiply the velocity into these many number of electrons into the value of charge to find out the current density. For current, you would ask me what is the cross-sectional area. Then if I tell you about the cross-sectional area, boom, there you go. You will multiply it by area. Simple. Okay. And there is a relationship between, now we are getting into the essence of the lesson. The most awesome part. And you'd be astonished to know that, what this kind of relationships exist and they make sense. They totally make sense. They're very intuitive. It's just like the colloquial language that we are speaking right now. Or the colloquial language that you're hearing. Okay. But let's, do a little bit of math around it to understand what is happening, to understand this, electrical phenomena. So, this both things is what we have talked before. That this is the drift velocity. How we are finding out the drift velocity? It's A into tau, A into time, and A is nothing but E by M, and you know this current density value as well. Just substitute them, manipulate them, work around the mathematics a little bit, and then you'll find out that it is nothing but NE, where E is the capital E is electric field by mass of the electron into tau, relaxation time. Okay, now I take this relaxation time inside and make an expression where I am able to, show a proportionality between the current density, which is a vector quantity. Current density is a vector quantity, isn't it? And then electric field E, or external electric field, whatever it is, like the voltage which creates this electric field. What do you expect? They should be proportional. There should be a constant. There should be a constant that should be driving this value. What is that constant going to be? Conductivity, makes sense? Conductivity is very intuitive. Let's say more the conductivity of the material, more is going to be the current density for the same given electric field. More the conductivity means more the ability to conduct. More the ability to conduct means more the flow of current. Less obstruction to electrons or less obstruction to any kind of charges. Very intuitive definition, very intuitive understanding of conductivity. And mathematically, if you work around, you will find out that conductivity is dependent on, or rather I should say, conductivity is nothing but Ne square tau by M. Okay, more the number of, free electrons, or more the number of free electrons per unit volume, more is going to be the conductivity. More that material can conduct. More the relaxation time, more the tau, means longer it takes to collide, which means the ability to conduct is more. And mass and E are constant things, they don't manipulate things, like conductivity much. They are not going to manipulate it actually at all. If you are talking about electrons, you are talking about different kind of particles they are. And what is conductivity? Conductivity is a material property. Do remember that J is equal to sigma into E, where sigma is nothing but conductivity, the way you represent the conductivity. And conductivity is a material property which is dependent upon the temperature, and like I'm talking about number of free electrons per unit volume, which is going to be material property again. Sometimes may not be, you can increase the number of electrons. And what about the units of conductivity? It's Siemens. You remember the company Siemens, the same thing. Okay, awesome, right? J is equal to sigma is an awesome concept, which is normal. It is the way it should be. And how do you derive it? You will make use of those two equations where you have related current density with drift velocity and drift velocity with electric field. And now let's explore something known as resistivity. Conductivity is the ability to conduct or allow the electrons or any charges to flow freely. Resistivity intuitively says that it should be an opposite, or there should be an inverse relationship between resistivity and conductivity. And you know what? Resistivity is equal to nothing but 1 by conductivity. That means there is a direct inverse relationship. Okay. And now again it makes sense. More the number of free electrons to conduct, means lesser the resistivity and lesser the relaxation time. More collisions means more the resistivity. And again, since conductivity was a material property and was dependent upon temperature, resistivity is also going to be dependent upon temperature, and it is going to be a material property. We'll explore this concept more deeply, in this lecture or the coming lecture, that, conductivity is inversely proportional to temperature and resistivity is directly proportional to temperature. If you keep on increasing the temperature, the collisions will be more. That means it will obstruct the flow of charges. And if you reduce the temperature, that means the electrons or the charges may be able to flow more smoothly. and conductivity is inversely proportional to temperature. And what is the SI unit of resistivity? You must have heard a lot about resistance. The SI unit of resistivity is ohm per meter. We will see why is that once we derive resistance. Awesome topic. Awesome topic, very colloquial language, very easy topic, easy to score. There's nothing complicated in this. Now let's do a confuse me challenge problem. This problem is about, conductivity and resistivity, the concept that we just discussed. So it says the conductivity and resistivity of the material was found to be A and B, and the electron density was doubled in the material at the same temperature. Then which of the following is true? Assume that increase in electron density does not increase collisions or other influencing factors. So the options given are the resistivity and conductivity doubles, the resistivity doubles but conductivity becomes half, or the conductivity doubles but the resistivity becomes half, and the resistivity and conductivity remains. Come on guys, come on, keep commenting, and more important thing is keep working out along with me, keep noting it down. These concepts are very, important. You may get it as a very small question, maybe in your BitSat or something, like in other exams, maybe sometimes in IIT JEE. As and when we keep moving to the lecture, you'll understand that IIT JEE problems are mostly confuse me challenge problem around this topic. In fact, they are confuse me challenge problem. I've seen one of this problem and I'll even show you that problem. It has nothing in it. They're just confusing you. They're just trying to confuse you and try to manipulate things here and there a little bit. But sometimes the answer is very easy. And IIT JEE is actually very easy. Most of the things it's either mix of concepts or either it's mix of different mathematical calculations, different mathematical topics, or it is basically very counterintuitive or intuitive concepts. They're trying to check your how you understood the concepts, and also about checking your pace at the exam. Checking up the pace at the exam does not make sense, but that also happens. So what has happened over here? The electron density was doubled, the number of free electrons per unit volume was doubled, and you need to find out what is going to happen to conductivity. Very intuitive. Doubled, direct relationship, conductivity is going to double, resistivity is going to become half. Okay? When temperature and rest of the factors, influencing factors are kept constant, or they are kept in such a way it does not influence. So it's option C. So now let's do the traditional way that we used to do before. How we used to derive V is equal to IR. We'll find the relationship between voltage and current. This is the form that we are more used to. If you're especially from 9th or 10th class, then you're more used to V is equal to IR, and then you're working on series and parallel combination resistors. And this is actually very much caught up in our brain that we are doing V is equal to IR. But rather it is also very important to understand how this R is and what is R. R is also something that is not like resistivity. We'll understand that as we keep moving to the topic. So you know this, let's do it conceptually. Let's not, let's derive this relationship conceptually, not, going through the equations, going back to the, the video or looking at your notes. What is I? I is current. How do you calculate from drift velocity? You need to find out the rate of flow of charge. Okay? Rate of flow of charge through a cross-sectional area. Not per cross-sectional area, through a cross-sectional area. You have, let's say, electron density per unit volume. Then you have area. You multiply them both. Then you get the number of electrons flown through the cross-section. Now you need to find out the charge. Charge would be multiplying it by the value of charge itself. In this case, it should be E or minus E. And you would multiply that by drift velocity to understand or to get the value of rate of flow of charges. That is nothing but I is equal to NEA into V drift. And what about the value of drift velocity? Drift velocity can be derived from the equation V is equal to U plus AT, where A is nothing but minus EE by M, the electromagnetic force. And if you take it in terms of voltages, it's going to be E is equal to V by L. Or V is equal to E into L, or E dot L, E minus E dot L rather. So it would be V drift is equal to EVML by tau. Now what I'm going to do is, I'm going to take this EV/ml by tau and substitute it here. Then you can see that I'm getting the relationship between voltage and current. And there is some sort of constant, like a material property constant, but also something more is involved in this. Something more is involved in this. Okay. So when I substitute it, I find out that I is equal to NE square A tau, where A is the area, N is the electron density, tau is the relaxation time, divided by ml, where m is the mass of the electron and L is the length of this conductor. In this case, we are calculating for this conductor, L is the length of that conductor. Length. Length means the direction along which the, like the electrons, to the direction along which the electrons are flowing. It should be opposite, or the direction along which the charges are flowing. Okay, length means the direction in which the charges are flowing. That length you are concerned about. Okay. And if you look at it, the length should be parallel to your area vector. Okay. But length is the absolute length that we are talking about. Now, I want to express it in terms of V is equal to something into I, or V is equal to I into something. Then what I do? I take it on the other side, this thing on the other side. Then I would get something like, V is equal to ml by NE square by into A into tau. Now, as and when the length keeps increasing, that means if I increase this length of this conductor, okay, then what is happening? If I increase the length of the conductor for the same potential, for the same voltage applied, I am getting lesser current output. Okay? And if I increase the area, if I allow these charges to flow freely, then I am getting more current. Without manipulating the length, if I am increasing the cross-sectional area, along the flow of, charged particles or electrons in this case, what is happening? Then the amount of current is increasing. Awesome? Makes sense? Let the electron flow for a longer length, they are going to undergo more collisions, more, the obstruction to flow of electrons. Increase the area, expand the area in the same unit volume. Then what is going to happen? These electrons are dispersed and they have more of a path and more of a relaxation time. Okay, the time between collisions will increase. And from this we know voltage is proportional to I, but there is a constant involved in it. Where the proportionality constant is affected by area, temperature, length, there should be also length, guys, and the free electron density or the electron density per unit volume. And that proportionality constant is something that you know very well, that is resistance. There is a difference between resistance and resistivity. We'll carefully have a look at it. So this, ml so and so, that is by NE square by A to tau is nothing but resistance. How did you derive the so and so? Intuitively think about current, intuitively think about drift velocity using Newton's first equation of motion, and then you will arrive to this equation. And do remember, E into L, E minus E dot L is equal to voltage. Okay, quite easy, very easy. This relationship, if you want, if they have asked you in terms of this, it's very easy. And do remember that if I increase, so if you want to remember the direct relationship, what is happening when I'm increasing the length, keeping the voltage constant, the current constant, then what is happening, then you can remember it, like if I'm increasing the length, then more the time, both the time the electrons have to flow for the same voltage, that means the lesser is going to be the current along the same material. If I'm expanding the cross section of the flow of current, the cross section along which the current flows, that means these electrons are going to undergo lesser collision. And if I increase the amount of free electrons, what is going to happen? There should be, for the same voltage, there should be decrease in current. Isn't it, guys? Isn't it really, really simple? Awesome. Let's get into the concept now. Now it says, we know this, what we have done is what we have just discussed. Okay? What we have just discussed. So basically, what we have done over here is, we have written like R as the resistance and then calculated. This is substituting values. And now I can do another thing. I know the value of resistivity. We just calculated the value of resistivity just earlier. If you go back, we just calculate the value of conductivity. Okay. Then from there we got the value of resistivity. And from, if you see that, it's like me ne square by tau. Okay, me ne square by tau. There I can, just make use of that, the same thing. And change it. Okay, basically substitute it, and then you will get a relationship between resistance and resistivity, which says that resistance is equal to resistivity into length. Length is the length along which the charged particles are flowing, and area is the cross-sectional area. Okay, it's very intuitive. And now the thing is, let's say I want to plot the relationships. But before that, let's have a look at this awesome diagram. You must have seen this diagram, where the home is trying, a very nice, like a cartoonish way to remember things. Like the ohm is trying to, resist the ampere, whereas the voltage is trying to push the ampere. What is happening over here is like this ampere guy is trying to get through the wire. The charges are going to get through the wire. But the ohm guy is saying, let it be. You need not move now. This is enough. This much speed is enough. Whatever. This much is enough. And then this voltage guy is trying to push this charges or the ampere. And what is the difference between resistance and resistivity, students? Resistance is dependent upon dimensions. You change the dimensions, resistivity is not going to change, whereas resistance is going to change. Okay? If you look at this, relation between resistance and resistivity, you will see that there is a dependence on not just the material property, but as well as the size and the dimensions of the material or the resistor or that any conductor that you're talking about. Okay? And we have talked about resistance. Then there should be something, there should be something known as conductance. Conductance is something that is going to, let me conduct more efficiently. Conductance is the ability of the material to conduct. So what they have done is, like they have represented, resistance with ohm, and they have taken the inverse of it and called it mho, spelled backwards. It's nothing but spelled backwards. And the thing is, conductance is going to be, resistance is going to be V by I. Whereas conductance is going to be I by V, which is also intuitive. More the conductance, more the flow of current for the same voltage. Okay, for the same potential, if I am applying the same potential using these batteries, then I know more current should be flowing for a material having more conductance, and conductance is also a material problem. Like dimension dependent property. It's size dependent property, it depends on area and length, but the other way around. Because it is directly, it's directly inverse of resistance. Awesome. Now let's, plot the graphs and understand these relationships, and these kind of graphs may be given in your exams. And even in your experiments, you do these kind of graphs. So, try to understand these graphs. Don't try to memorize them. Graphs is something that you should never memorize. Even sometimes it is okay if you memorize formulas, because sometimes you will have to memorize formulas. But graphs is something that, it's a graphical, pictorial representation. It's showing that phenomena in sort of x and y axis. And that x and y axis has a lot of information in it. So most of the, theories or these equations are derived around graphs. Like they plot it on graph and then they try to find out the relationship using that geometrical shape. But that being said, what is the relationship between current and voltage when current is plotted on so the current I is plotted on x-axis and the voltage is plotted on y-axis. If this is the relationship, this blue line is the relationship between them, between these two, between the current and potential difference, and it forms an angle theta with current, then What does it tell you? This is y, potential is y, current is x, y is equal to mx, where m is the slope, and v is equal to I into some quantity, that is slope, which is nothing but tan theta in this case, which is going to be resistance. Okay, tan theta, that is tan of the inclination, is nothing but resistance. Awesome. Let's get into the relationship between resistance and resistivity. Let's say they have given you a graph where they have plotted resistivity on the x-axis. It can be the other way around too. Just remember this. It can be the other way around just to confuse you, just to create that sort of confusion in your mind. So be mindful of those situations where they are keeping this value on the y-axis instead of x-axis. So now we are plotting the resistivity on the x-axis and the resistance on the y-axis. And again you find that there is like a line that is passing through origin, and it has like a slope, and it forms an angle theta with the resistivity axis. So what would be this time the slope denoting? What would be the theta denoting? Both are material property, but resistance has something additional to it, that is the dimensions or the size or the physical size of the material matters when you are calculating resistance. So now this slope is nothing but you can make use of that equation, r is equal to rho into L by A, and then or else you can also think intuitively, that is more the area, less the resistance, more the length, more the resistance, and come to this conclusion that this tan theta is nothing but L by A, length by cross-sectional area, which is proportional to theta. Okay. Now let's say I am plotting the voltage on x-axis and current on y-axis. What is happening in this case? Very interesting graph. But something else is different over here. This time, this theta is not directly talking about resistance, because potential is plotted on x-axis and current is plotted on y-axis. Keep noticing this kind of things in your exams. Graphs value might be the axes might be inverted, or they are changed. Then the meaning itself becomes very different. Okay. In this case, what would be the tan theta? Tan theta is going to be y by x, I by v, which is nothing but conductance. So tan theta is conductance, which is proportional to theta. A small interchange, but a big, change in terms of slope. Awesome. Makes sense. Let's say I'm increasing, the potential, the current should also increase with a constant conductance. Now let's do a confuse me challenge problem. Very, very interesting problem. Awesome problem. Guys, keep commenting. Keep doing it along with me. This should be something that you should answer in a moment. It should not take you much time to answer this kind of problems. Okay. The resistivity of a cubical conductor block was found to be X. The area of the block was halved. Then the new resistance, rho nu is how much? Okay, they are manipulating the dimensions of a block, and what they are asking you is how the resistivity changed. Is it 2x if the earlier resistivity was x? Is it x, or is it x by 2 or x by 4? Come on guys, come on, it's easy. There's nothing to think in this. It's basically a concept, that's it. So the resistivity does not change. Resistivity remains the same, it is independent of the dimensions. It's a material property. It's property of that each, material, like the small elemental materials. Now, here's a challenge problem where what they're doing is the resistance of a cubical block was found to be y, and the area of the block was halved and the length was kept constant. Then the resistance R dash, then the new resistance R dash is. So in this case, what they have done is there is a resistance of this cubical conductor. They did something to make and they probably cut this cuboidal conductor to make it into half. They made sure the length is same. If the current is flowing along this length, the length is same, and the area was halved. What is going to happen to the new resistance? What is the new resistance? You don't even need to know about the formulas and etc. If the length is kept constant and the area is halved, that means the material is going to face more resistance. Okay. Rho is equal to L by A is something that you can use, and you know that A by 2, you can come to the calculation where if the resistance was Y, now the resistance is going to be 2Y. But guys, do remember this is a very hypothetical problem where they haven't talked about, the electron density. If the electron density is kept constant, that should have been said, then this makes more sense. The same halved area. Okay. Awesome. Or else you can also think about it as, a resistor where the, area is halved, and then you'll see that the same thing is happening. Like the resistance is becoming twice more, the resistance is facing a conductor entering into that conductor. Awesome? Easy? So a challenge problem. A cylindrical wire of R ohms is stretched to double its length. Then its resistance in ohms is. Ignore stress and strain. Any deformations. Okay? Any sort of other deformations, I mean. So there is a cylindrical wire. I'm stretching it to double its length. Okay. Initially I found that the resistance before stretching it was R ohms. What is going to happen to the resistance? Come on guys, keep replying, keep commenting, keep writing it down. Easy questions. These kind of questions may come in your exams and will come in a few of your competitive engineering exams. So I'm doubling the length while keeping the material the same. I mean this material the same, this particular material. I'm not talking about the material property, the material itself. Once I'm extending it, the area is also going to change. The cross-sectional area is also going to change. Okay. If I'm stretching it double the length, the area is going to become half. The volume should remain constant. The mass and density are constant. That means the volume should remain constant. So you equate the volumes. In simpler terms, if the area is doubled, 2L into A dash is equal to A into L. That means the A dash should be A by 2. Okay. Now, what is going to happen to the resistance? That is going to become 4 times. Because you have doubled the length, you have also half the area. Okay. You half the area and double the length, which means more resistance, 4 times the resistance in this case. Easy? Awesome? Simple? So this is just the calculation that we are doing. The same thing is done over here, nothing different. So let's get into the challenge problem. Next one, or the next challenge problem. A cylindrical wire of R ohms is stretched along the cross-sectional area to triple its cross-sectional area. This time they're stretching it along cross-sectional area. Then the resistance ohms is. Guys, quickly, the answer is very, very easy. I have stretched it along cross-sectional area. Then the length is also going to change. If I made this cross-sectional area 3 times, then the length has come down by 3 times. And the resistance has gone down by 9 times. So options given are R by 3, 3R, 9R and R by 9. So the resistance has come down by 9 times. This should be the correct one, D. Easy? Same cylindrical wire. In this you have just stretched the cross-sectional area by 3 times, tripled its cross-sectional area, and the length would come down by 3 times. Okay. Awesome, easy. Now this is a JEE Advanced challenge problem, guys, and look at this problem very carefully. Very, very carefully. This has nothing huge in it. This has nothing awesome. I mean, like, it has something awesome in it, but it has nothing difficult in it. See, some of this, your IIT problems are going to be something like this. Easy, intuitive, need not think much. And especially if it's, like a low mark, if it has not too much weightage, it's not like 10 marks, 20 marks, like the paragraph based problem, then the questions are very easy. The answers to these questions are very easy. Consider a thin square sheet of length L and thickness T. Consider a thin square sheet of side L and thickness T made up of a material of resistivity rho. And the resistance between the opposite faces are shown by the shaded areas. Okay, so this is that, like the conductor. This is the material that is going to conduct. The current is flowing between the shaded areas, and this is length L and this is thickness T. So now what they are asking is, tell us the relationship between the resistance and the two opposite faces. Okay. What is the resistance proportional to? Whether the resistance is proportional directly to the length L, or it is proportional to T, or it is independent, directly proportional to T, or it is independent of L, or is it independent of T? See, something has been given in just in terms of geometrical terms, that has confused the problem a little bit. So it's square sheet. Square sheet means this is L and then this is also L. Not very nicely represented, but this is L, this is also L. And once you take for a constant resistivity or a resistivity of material, resistance is equal to rho L by A, you know that A is nothing but L into T. Because current is flowing in this direction. This is the cross-sectional area, L into T. Rho into L by L into T means it is independent of length L. It is basically mathematically talking is independent of L. That's it. Such an easy problem. And what they have done is they have just introduced a square, a thin square sheet. And at the moment, at the moment of exam, things look confusing. But you can just notice these kind of things. That's why we are discussing this, right? Awesome problem though. It's a mathematical problem. It's a one-liner problem. One-liner problem that is probably going to give you 3 marks or 1 mark. I guess I'm not very sure, but I think it's 3 marks. It's basically only one-liner problem. That is it. Now this is an awesome challenge problem, guys. Here a graph is given to you. Okay. And where potential is plotted on x-axis and current is plotted on y-axis. Okay. Current is plotted on y-axis. Something has been changed a bit. Come on guys, I need the answer now. Find the resistance from the VI graph. Students, it's very easy. Very, very easy. Just the problem, just the graph has been given in a very counterintuitive way. Okay, the slope of this line with potential difference has been given to you. You are given the relation of I by V. You take tan theta. If you take cot theta, it is going to be V by I. And cot of 37 is nothing but, what is cot of 37? Cot of 37 is going to be 4 by 3. So you should also, make sure that you remember the tan value, sine value, cos value and cot value of 37 and 53. Because nowadays these are being introduced in the exams, even, without giving the value. So that becomes, at that moment it becomes a little tough. So you have to memorize tan 37. There is a trick to play around it. I spoke about it in kinematics. There is 3, 4, 5. You can play around it to understand the value. Okay. Awesome, easy. In this case, what did they manipulate? Current is plotted on y-axis. People generally are assuming, this theta is like, tan theta. Then I go do this tan theta. Then tan theta is going to be V by I. But rather in this case, it is I by V. And rather you have to do the cot 37. It is going to be 4 by 3. Easy? Now, let's get into the next problem. This is somewhat of a theoretical problem. Like you are given a diagram, awesome diagram. It's a hollow cylinder of length L and it has an outer radius B. This outer radius is B. This entire part is hollow. And then the other thing that is given to you is the inner radius is A. Okay. Calculate the resistance of the tubes between its end along length L for a given resistivity rho. How do you do this, guys? Typically, you know what, for calculating, resistance from resistivity, you would have to integrate it. This is standard thumb of rule. Just like how you did integrate for, finding out, from a given current density, the current, or for any such elemental based problems, you are going to do the same thing. But in this case, you need not worry about it. They have told that it has a uniform resistivity. All you need to know is the area of this ring. That is it. You need to know the area of the ring. And basically, what did you do? Keep answering it, guys. This is a very simple question, I know that, but keep answering it and keep writing it down. If at all you come across a complicated problem, put your pen on the paper. Else, try to solve it in your mind and try to reply quickly. And that would also get you to act fast during the exams, and try to understand the intricacies that we are discussing during this entire session. During every single session, we are discussing such intricacies, right? You should keep on noticing those intricacies. These are being discussed specifically for your exams. Okay, if you're a hustler, you are enjoying it, you're looking at it, wow, awesome, these kind of problems are there. Okay, if I plot it, then I'm making some mistakes in my experiments or something like that. You're preparing for exam, notice these things very carefully. So in this case, the resistance is going to be rho into L by A, and A is nothing but this area of the cross-sectional area of this ring, which is pi into B square minus A square. And it would be rho into L divided by pi into B square minus A square. So it would be option D. Okay, easy, very easy. Okay. Again, a previous year IIT JEE problem, and if you keep noticing the problem around resistance, resistivity, conductance, conductivity and current, these relationships are just given like a confuse me problem. It is not much different than confuse me problem in IIT JEE when we are specifically talking about these kind of relationships. Okay. A steady current flows in a metallic conductor of non-uniform cross section. A quantity or quantities constant along the length of the conductor and is R. So it's and is just basically English. So the quantity constant along the length R. The quantity is constant along the length R. Whether it is current, electric field, drift speed, or just the drift speed, or option C says current and drift speed, and D says current only. Nothing, guys. There's nothing too much to think about it. Actually, just keep replying. Keep writing that down on a paper. There's nothing too much to think about it. It's actually a very simple problem. In fact, let me tell you something. The hint exists in the question itself. This is a previous year IIT JEE problem, and you are noticing again a problem where they are confusing you. A steady current flows. A steady current flows means the current is the constant thing. Okay. They haven't talked about electric field. They haven't talked about drift velocity. And the drift speed is also dependent upon electric field. And they may not be constant along the length. The constant along the length is steady flow of current. The steady flow of current was the input in the question. Earlier it was square. In this case it is steady flow of current. Awesome. Easy. Now, this is actually not a confusing problem. But let's call it a confuse me challenge problem. The length of a conductor is halved. Its conductance will be double, remain same, half, 4 times. Quick, guys, quick. The length of the conductor is halved. The length of the conductor is halved means the conductance should be increasing or decreasing. It should be increasing. It should become double. Okay, you can remember that formula and do it, remember that it's an order 1 relationship between, inverse of length and conductance. Since you halve the length, conductance has become double. Don't go mathematically, go conceptually. Easy. Conceptually things become easy, but you have to do the mathematical manipulations at the end of the day. Okay. And when it comes to IIT JEE, you're going to mix the concepts and do the mathematical manipulations. Awesome. Now let's get into challenge problem. A wire of length L and cross-sectional area A is having a variable resistivity rho that varies along its length as rho is equal to rho naught into 1 plus x by L. Calculate the resistance of the wire. So the beauty of this question is, along all this length, the resistivity is varying this time. The resistivity is not constant. Now you need to find out the resistance. Come on guys, keep doing this. This is a very interesting problem. Actually a very easy problem, very interesting problem. What would you do? You would take elemental areas. You'd consider an elemental area and solve this problem. If I take an elemental area, I would consider the length of that elemental area as dx. Assuming area is constant, you'd write it as that r is equal to rho into L by A, or rho naught into 1 plus x by, r is equal to rho into L by A, which is nothing but rho naught into 1 plus x by L into the L by A thing. Okay. And in this case, L is going to be dx and area is going to remain area. Okay. Because the rho is only varying along length. And even if you look at the equation, you will come to know that the resistivity is only varying along length. So you do that, simply you can do, what you can do is you can simply multiply this rho into dx by A and calculate it. This is going to be rho naught into 1 plus x by L into dx, and by A you can take out that rho naught by A as common, and then you do, like dx into x into dx by L and integrate it from 0 to L. You have to integrate it from 0 to L. So in these kind of problems, you have to assume it starts from 0 and it ends at L. Okay. So that would be rho naught by A, x, after integrating it would become x, and the other term would become x square by 2L. And then you would calculate it for L to 0. So that would be L plus of 2L. L plus of 2L into rho naught by A. That's going to be 3L rho naught by A. Okay, 3L rho naught by 2A, I guess. So it should be like, so that was like, L square by 2. So okay, 3L rho naught by 2A. Because it was L by 2, not 2L, L by 2, L by 2. Okay. You can do this thing like, you differentiate the equation to find out whether the integration is correct. Okay. So this is what is given over here. We have taken an elemental area and we have thrown the values of rho and we have integrated from 0 to L. And when we do that, you get that, it is nothing but rho naught by A into x by x square plus 2L. And you do it for L, then you find out it is 3 into L into rho naught by 2L. Which is going to be option B. Okay, easy, awesome. Now let's get into the next one. So this is a very interesting problem, guys. Like this one is about a truncated cone. People also call this frustum. A material of resistivity rho is in the form of truncated cone with height h. With height h, on the top end A, radius is A, on the bottom end A, radius is B. Basically, have a look at this diagram. This is a truncated cone or a frustum which has height h and a varying cross section where at one end it has radius B which is more than that of radius A. Okay. Let's say this area is varying uniformly. Generally, when it is not said that the area is not varying uniformly, even it becomes very tough to solve for anyone. But If it is not set, then the area is varying uniformly from A to B. Okay, we have to find the resistance along the height. So this is the cross-sectional area. This is going to be the height or length of the conductor. So now in this case, there are a couple of methods to do it. In fact, 3 methods to do it. One, you can take y is equal to mx plus c, which is a little complicated one. You can take y is equal to mx plus c. You can take this as theta or do it in a simpler way. You can take this as tan theta. Tan theta should be constant. You always know the value of this. Then you would have 2 triangles and then you can do it. Or else, I'll tell you a very easy shortcut. For such frustums, it has been found out A is nothing but under root of A1 into A2. For such frustums, it has been found out that area, the total integrated cross-sectional area for a given constant resistivity, if it is a constant resistivity, you can do this. If it is not a constant resistivity, you have to go by y is equal to mx plus c rule or calculate the tan theta, for those triangles and apply them. So what is it? Area is equal to under root of A1 into A2. And in this case, area 1 is pi A square and area 2 is pi B square. Under root of pi A square, pi B square is nothing but pi AB, and you know the length h, so that would be rho into h divided by pi by AB. So this is a shortcut. Do this problem properly, make use of tan theta. What if we get a problem around varying resistivity, then this may become a problem. Or let's say varying area and they are given an equation for area. So work around those integration kind of problems when they are talking about resistance to resistivity or current density to current, and these kind of problems you need to work around integrations. Quite easy, quite intuitive, very easy problem. So that is what is written over here. The truncated first term of the cone can be written as under root of A1, A2. So it's easy, it's pretty easy problem. Awesome. Now this is a very interesting challenge problem. The figure shows that the cross section through 3 long conductors of same length. Okay. These 3 conductors shown in the figure A, B, C have same length, okay, with the cross-sectional, okay, with same length and material with square cross-section of edges, okay, and A is an hollow, like a cuboid, such that it can fit the B, and B is a hollow cuboid such that it can fit the A. So this can go inside this comfortably and this can go inside this comfortably. And they have even given us the area of A, B and C. I mean like the length of A, B and C. This is root 3A, root 2A and A. Okay. Now calculate the relationship between the end-to-end resistance. They are asking you whether the resistance of A is greater than that of B of C, or whether all the resistances are equal, or whether it's the other way around, where C is greater than that of B and of A. Or there isn't enough information to determine the value. Come on guys, come on. This is an easy one. This is an awesome and an easy one. This is such an easy problem. And you know what? The answer is also a little bit intuitive if you just work around, what is the area difference, like what is the area through which it is flowing. Okay, root 3A is given as the dimension. The area would be, the area through the cross section through which in A it is going to be flowing is going to be 3A square minus of 2A square, since this can exactly fit in. Since this can exactly fit in, that means this length is going to be under root 2A. Okay, and the area would be A squared for A, and similarly if you do it for B, it is going to be B square, A squared, and for C, it is A squared. Length is same, area is same, resistances should be same. Little bit tricky, just in terms of putting it inside and putting it inside, that is making a little bit confusing, but very easy problem. So resistance of A is equal to resistance of B is equal to resistance of C, which is nothing but rho into L by A square for all 3 of them. Awesome question. Actually, pretty awesome question. Very interesting question from the given graph IV, where I is plotted on x-axis and voltage is plotted on y-axis. Which part has the highest conductance? Which part has the highest conductance? Whether it is A, B, or whether it is C, D, or whether it is B, C, where the slope is becoming a little bit going to the peak, or whether it is D, E. Okay. Answer this question, guys. Answer this question. It's 10 seconds or a half a second question, maybe like 2 seconds question, just looking at the graph or reading the question. The entire question may take 30 seconds to 1 minute. Quite easy, means quite easy. The relationship between I and V is given and it is in the form of y is equal to mx. You can assume it is in the form of y is equal to mx. Neglect this curvilinear paths. Now, there is a specific point in this graph. There is a specific point in the graph where the slope is in the opposite direction. If you notice that point, you know that at this point, resistance is decreasing with voltage. Okay, resistance is decreasing with, increasing current. Okay, this tells you that CD has the highest conductance. Easy, awesome. These kind of graph kind of questions you can expect in your exam. Awesome, guys. It was pretty awesome. I think this lecture was very much interesting. And remember, this is independent of much of the syllabus. But in exams, you can expect something around, moving charges or something like that. Or, like electrostatics. But this was a very easy problem, very intuitive, very easy, topic. And keep enjoying it. Kill your ego. Love people. Value love. And keep valuing love. Keep smiling, guys. Keep smiling. Avoid gossips. Be it your exams or even if you're relaxed. And you have to work hard to achieve that success. It's about that 99% perspiration. And also remember that this topic is not about 99% perspiration, but about 99% practice. Which again comes down to 99% perspiration. But to understand, you need nothing but just inspiration. And knowledge, keep acquiring it, keep sharing it, keep sharing this channel. If you like the video, like the video, share the video. Awesome, guys. Discuss with your friends, brainstorm with your friends about these concepts, and also talk about this channel to with your friends. Awesome, guys. Awesome session. I guess you understood everything. If not, do let me know. Do comment. And awesome, guys, we have something interesting for you. That's our Unacademy Learning app. You can go to Play Store and App Store and download our Unacademy Learning app to attend special free live classes with our top-notch educators. And you may want to do that. And you can also go on to a subscription platform if you're looking for some test series, live quizzes, or live interaction sessions with top-notch educators. Or if you want to, get your doubts cleared, which is also very important to score in exams. And you can get our subscription for hardly, for a 24-month program, it's 1,500 per month. And you can apply the coupon Murli to get a 10% instant discount. Awesome, guys. Keep enjoying it. Keep loving everything. And keep smiling, guys. Keep smiling. Stay safe. Bye-bye. Take care.